Here we see all components that we've seen so far, which is the instruction memory, the register file, the ALU and the data memory all put together. And this would be what we call as a single cycle implementation of the data path and control. So we load an address from the instruction memory. The instruction is located in the program counter and we read the address. The instruction is then given to the control unit to decode. The register access is implemented where we read the values contained in the register. We compute the effective address, or we compute the arithmetic operation that we are interested in, and then we may or may not access the data memory, and then we write the value back to the register file. And this would be a single cycle implementation, so everything takes one clock cycle. The good thing about a single cycle implementation is it is easy, it is simple to design, and it is easy to decode the signal. The bad thing about this is you would take the same time that the longest instruction would take, and that would be your clock cycle time. For example, if you are thinking of an instruction like a load word, then you probably would need the instruction memory to load the word. You would access a register file to read the base value. You would compute the effective address. You access the data memory to read out the data and then write to the register file. This would be the longest instruction, and the time it would take would be the time for the entire instructions, which may or may not take make use of all the functional units. So one way to optimize or improve this is to break this into multiple clock cycles. So we could design in such a way that different functional units are active at different times. And we could design a complex finite state machine which decides how the data path and control should flow for different instructions. The implementation of that would be more complex, but then different instructions will take different clock cycles. So if you do that, we can break this down into 5 cycles or 5 components, and those would be the instruction fetch, where we fetch the instruction decode and register fetch. We find out what the instruction is so that we can set the control bits, and we fetch data from the register file. We execute in the ALU or calculate the effective address if it is going to be a memory access, or we could also decide whether we should branch or not. Now, if you look at the ALU, we have a choice for the data read data to, and the sign extender. Now, if you're going to do an effective address calculation, then you probably would require read data 1 and the sign extender. If you're doing some arithmetic operation like DAD, R1, R2, R3, then you are going to be reading value R2 and R3 from read data 1 and read data 2. Now that multiplexer is controlled by the signal ALU source. So this ALU source is decoded in the instruction decode register fetch stage, where we figure out what the value of this ALU source should be, whether we should read value from the read data 2 or we should get data from the sign extender. Then you have the ALU control. ALU control is mostly to decide whether you're going to implement some logical operations or arithmetic operations. And we have the memory write and the memory read signal, which we mentioned is to read a value from memory or write a value to memory. The last one is the memory to register, which we call as a write back stage. Now in the write back stage, we have a choice where we read the value from the data memory, or we'll get a value from the output of the ALU. Now in certain cases, let's say it's an R type instruction, DAD R1, R2, R3, there is no data memory access. So you can bypass the data memory stage and you can go straight to the write back, where you can select the value with memory to register set to 1, and that value is what is written to your register file. So the 5 stages here are instruction fetch, instruction decode and register fetch, execute or address calculation, memory access, where we access a value from the data memory, and the write back stage. So we break our single cycle data path into 5 distinct components. And one of the ways we can break this further and improve performance is looking at a technique called pipelining, which is coming up next. So in a pipeline design, we can see that the bandwidth, or what we call as a throughput, is the number of tasks completed per unit time. And our goal here with pipelining is to improve the throughput. So for a system that is going to operate on one task at a time, generally the throughput is inverse of the latency, right? So if you say the latency of the task is 5 nanosecond, the inverse of it is 5 gigahertz is the throughput of it, or 5 gigabits per second is another way of looking at it. But programs generally include billions of tasks or instructions, right? You're executing billions of instructions for any given program. And the idea is to see if we can overlap execution of those instructions so that we can eventually improve the throughput of the system. So pipelining, basic technique of pipelining is overlapping tasks by breaking their execution in smaller stages. So if you have one long task, which is what the single cycle stage pipeline design looked like, break it down into smaller chunks. And as you break it down into smaller chunks, you can improve the throughput or the bandwidth. Throughput generally will increase if there are many independent tasks. So one of the very important points of pipelining is there should be sufficiently large number of independent tasks or instructions. And that is not an easy task. Latency required for each task may increase slightly because as you create or as you increase the number of stages, you will have a tendency where you may have to create some simple digital components such as latches, which may increase the cycle time a bit. So there is a cause where the latency might increase because of your design. The hardware costs mostly remain constant. That is, the amount of combinational and sequential logic required to implement any of the pipelining components, they don't change much. So you have this hardware fixed cost, and then you break this down into smaller chunks. And the more chunks that you have, you're going to have higher bandwidth or higher throughput. So here is a visual display of the same idea. So if you want to illustrate pipelining, this would be a simple combination logic. And this combination logic has n gate delay. So we're looking at all the gates which are connected in series and say this is the total time for this particular input to arrive at the output. At the beginning we have a latch. This is controlled by a clock. When the clock is applied, signal is available for the combination logic. It goes through n gate delays and the output is available. The bandwidth of this system is approximately 1 by n, where n is the number of gate delay. So obviously it depends on what is the duration of the gate delay and so on. But if there are n gate delays, we can say the bandwidth is approximately 1 by n. Now the concept of pipelining is to break this into smaller chunks or smaller stages. So in the next one we will see that if we divide this to the n gate delay into 2 n by 2 gate delays. So instead of one big n gate delay, we have now 2 smaller n by 2 gate delays, and these two are separated by a latch. So what would happen is the signal would first work on the first n by 2 gate delay, and then at the next clock it will go to the next n by 2 gate delay. If you look at the hardware cost between the two, there's not much of a change. It's similar n gate delay that you're looking at, which is broken into 2. But if you look at the bandwidth now, that is the rate at which things are completing, it is approximately 2 by n. So we have double the bandwidth by breaking it into 2 stages. Now what we have added here is a latch, which is shown as a L. Now latch is a component which is like similar to a flip-flop, right? Where on applying a certain signal, the input arrives at the output. So you generally apply a clock. When the clock is rising or falling, the input value that is available at the latch arrives at the output, and the next n by 2 gate delays can work. Now you can do the same thing, that you could break this further and say from the first n, you could say n by 3 gate delays followed by a latch and so on, the bandwidth now increases to approximately 3 by n. So by doing similar smaller stages, you can increase the bandwidth which is approximately equal to the number of stages. Now the trick here or the catch here is as the number of stages increases, the number of latches also increase. And each of these latch has a very small delay. But with more number of stages, the latch delay also begins to play a big role. So there is a point of diminishing returns if the number of stages explodes, because now you will see more and more latch delays. And this was one of the basic premise of going for higher number of pipeline stages. For example, Pentium, when it came, Pentium 4, they were looking at 10, 15 stages. They were targeting even 20 stages, so that the more number of stages would imply higher throughput. And of course, you at one point in time, the latches would start playing a role. But the goal was that you wanted higher throughput, and the more stages generally allowed you to do so.